hackathon presentation from team Extreme Devs. Let's explore the two-body problem. I'll show a two-body gravity simulator with high accuracy integrators, collision, analytics, and ready-made templates. We can start from curated scenarios. Here are many curated scenarios. Let's start with the circular orbit. So now we can see the circular orbit simulation. There are many other scenarios. Let's see the equal mass binary scenario. Now we can see the real-time interactions. I can drag this. The center of mass changes, also the position changes. Also, when I increase the mass, it also changes in real time. Also, when I start the simulation and I drag them, this also changes their behaviors. So there are two main concepts. I can drag with my mouse, and shift drag changes the velocity. Shift drag changes the velocity. So these are the interaction controls. Now I'll show the physics controls. There are vectors like velocity vector, force vector, displacement vector, position vector. We can see all of this. Let's start and let's see how different vectors interact with each other. There are multiple integrators we have implemented like velocity worldlet, Lange-Kutta 4 and RK45 adaptive and semi-implicit Euler. Velocity worldlet is great for long-term energy stability, RK45 for high precision around close approaches. Body parameters. Let's see what body parameters we can change. We can change mass, xy position and velocity for both of them. Now let's see the analytics. There are live states and there is a HUD which shows real-time energy graphs and velocity graphs and distance graphs. So these things are modeled in real time using graphs. So there is also a escape detection mechanism. Let's see the hyperbolic flyby to simulate the escape mechanism. Now let's simulate an unbound hyperbolic flyby. Let's see the time to escape, velocity to escape and relative velocity. Let's start. And the time to escape is 2 and velocity escape and other real-time analysis is also shown here. The COM also changes real time with our movements. There are two COM modes, COM frame and lock COM at center. Let's see these two modes where we lock COM at center. Now let's see the collision detection. For this, I will use the head-on collision scenario. Let's load the scenario and enable collisions and make our softening factor to 2. Let's see the collision now. So it was, now let's decrease the softening factor. Now the collision was stickier than before. So this was our features from the two-body gravitational problem. Now we will switch to our simulation problem. Welcome to Projectile Motion Simulator. We'll explore launches with and without air resistance and see live graphs. Controls are on the left and simulation is here. Graphs are below. Quick controls and data overlays are on the screen. Let's do a baseline launch at 50 meter per second, angle 45. It will draw the, let's disable the air resistance for the baseline simulation. So this was a baseline simulation without any air resistance. The full trajectory was drawn and the metrics was real time and instant. Let's see another time, real time metrics and also the launching trajectory. When we enable the prediction, we can also see the prediction. Let's animate the launch to watch the motion unfold. So this was our basic baseline simulation. There are graphs below the velocity versus time and height versus time and acceleration versus time graphs also update live. So there are also a quick control like prediction, solver switch and other like grids and air resistance like things. Let's change the initial conditions now. Let's give it to 30 and launch another one. This also looks pretty good. So I can also raise the launch height. By raising the launch height, I can simulate from a higher ground. Now let's enable our air resistance and configure our drag parameters. Let's keep CD at 0.47. Let's pause it or it will update real time. When we play it and update the factors, it restarts and starts from the beginning. So let's start one with air drags. So air density 1.225, area 0.01. With drag on, the solver automatically switches to a numerical method like Euler or Runge-Kutta 4 for more accuracy. So the prediction is on and we can see our ball is not going in the predicted path, rather taking another path. The acceleration model now includes quadratic drag. We can see the equation here and also the acceleration graph. We can compare different numerical methods like Euler and then Runge-Kutta 4. Reset brings everything back to baseline values. Let's play a run and watch the live vectors and HUD. Let's enable the air resistance. Now see what happens. It didn't follow the predicted path. That was the presentation from our side. Thanks for being with us.